This video looks at how you will predict with step response models. So the previous video focused on Karima models and how you would form prediction matrices and equations for Karima models. However, a step response model is similar and often a lot more readily available in real industrial scenarios. So you might say, well, what happens if I want to use a step response model? This video will show how with minimal adjustments you can use the same code and concepts as we use for Karima models in order to find the predictions with step response models. Now, for convenience, the typical unit delay that's in the step response and the impulse response is absorbed into the algebra, so don't worry if you don't see it explicitly. Karima model then. So what we did in the previous video is we looked at how you would predict with models of this form: A delta y equals B delta u. Now, a step or an impulse response model is very similar in structure. It's still based on Z transforms, and the main conceptual difference is that the poles, the A of Z term, is transferred to the right hand side of the equation. So if I do that, you'll see I can rewrite the equation like this, as delta y equals B over A delta u, or alternatively I can write it as H delta u, where H equals B over A. Now, I think that's what that says there. So clearly H of Z here represents the impulse response of the system. Now, no, not the step response, it's the impulse response. So I can write delta y equals the impulse response H of Z times delta u. What we want to do now is say, okay, can I form the prediction matrices using exactly the same technique as I did in the previous video with a Karima model? So I've got delta y equals H of Z delta u. And so what I can do, if you just look up the results of the previous video, by inspection I can say the prediction equations have to be given by this expression here. I've got C delta inverse times CH, and that's times delta u future, C delta inverse times capital H subscript H delta u past, and I've got a C delta inverse H delta times y past. So I can do that by inspection, just using the previous video. But we've got a bit of a problem here. We want to compute the matrices H, P and Q, and you'll notice in essence this one is H, this one is P, and this one is Q. We want to compute these matrices based on the step response coefficients, because that's the information I've been given. But so far, everything we've done is been based on H of Z, which is the impulse response. So I've got H equals C delta inverse times CH, but CH is the impulse response. P is C delta inverse HH, again, H is the impulse response. This one has just got deltas in it, so it's somewhat easier. However, this is where we get a nice advantage. The step response and the impulse response are actually very closely linked by a simple formula here. The step response G of Z is simply the impulse response H of Z divided by delta. So I've written that formula out here for you. Z inverse, I've got H of Z over delta. Now if I actually carry out the algebra for that, what you'll find is my definition of my H matrix was C delta inverse times CH. And what do you notice? This is exactly equivalent to what we've got up here. So in fact, my H matrix is the Toeplitz matrix of the step response coefficients. So the H matrix in fact was based on the step response coefficients if I'd only noticed. So that's nice and convenient, so I can just write H down as the Toeplitz matrix of the step response coefficients. What next? We can also see that the Q matrix was given as minus C delta inverse times H delta, and I've missed a minus sign there, which is essentially just minus L. So Q is just a vector of 1s. That's for this ESO case. For the MIMO case, a vector of a matrix of identity matrices. But again, the Q I can write down by inspection. So you'll notice in both cases here, no computation at all. To get the H matrix, just write down the step response coefficient straight into the Toeplitz. For the Q matrix, just do a vector of 1s. However, there's one other thing we've got to look at. What about P? P was given as C delta inverse HH. And this one is not quite so straightforward. First of all, we know that C delta inverse is a lower triangular matrix of ones, and I'm going to use that observation. And therefore, if we construct P, and I'm going to multiply it out longhand so you can see what's going on, this is what we get. First of all, HH, which is based on the impulse response coefficient, looks a bit like this. Now, I've not filled in everything here. Clearly, it goes on down as well if you need a longer horizon. If I now do C delta inverse times HH, I get a matrix that looks a bit like this. An interesting structure, if you think about it. You see I've got H1 in the top row there, then H1 plus H2, then H1 plus H2 plus H3. If I go to the second column, you see it starts on H2, H2 plus H3, H2 plus H3 plus H4, and so on. Very nice structure. But again, still based on the impulse response coefficients. How can I relate this to the step response? Well, as it happens, it's quite straightforward. If you look at the step response coefficients, there they are, G0 plus G1Z inverse plus G2Z inverse and so on, then what you find is they're related to the impulse coefficients like this. H0, so H0 and G0 are the same. What about the next one? G1Z inverse is actually H1 plus H0. G2 is actually H2 plus H1 plus H0. So you see there's a very simple relationship between these different coefficients. So I can use that because now if I look at the matrix I've got, this one here, which is C delta inverse HH, what you'll find is the coefficient H1 is actually G1 minus G0. The coefficient H1 plus H2 is actually G2 minus G0. The coefficient H1 plus H2 plus H3 is G3 minus G0. If I now look at the next column, H2 is G2 minus G1. H2 plus H3 is G3 minus G1. H2 plus H3 plus H4 is G4 minus G1, and so on. And so clearly there's a pattern here. So what you notice is there's a clear and simple dependence on the step response coefficients, which is what we needed. And crucially, these all converge to 0, so we can truncate after a given number of columns. So what's the summary? What we're going to do is we're going to form the prediction matrices using the step response coefficients. So I can write down, first of all, that my prediction matrix with step response coefficients is given like this. Y future is H delta U future plus P delta U past plus L Y past, and what you can see is H is basically the turplets of the step response parameters, L is just a vector of ones, and P is based on the differences between step response coefficients, and I've written down the details there, but the key thing is you can write them all down by inspection given the step response coefficients. So in conclusions, it's straightforward to build predictions given the step response coefficients, and therefore this may be logical where those coefficients are readily available. And clearly you'll get unbiased predictions in this case because we've essentially based it on the Creamer model. And the main weakness of this method is the P matrix, which gives the dependence on past inputs, may have a very large column dimension before the coefficients decay to negligible values. So there's a lot more parameters to carry around, a lot more matrix multiplication. But the definition of the actual prediction matrices is by inspection. There's no computation at all really, apart from a few subtractions. As a warning, it's implicit that step response models can only be used where the system is open loop stable.